So yesterday we were, we ended on this slide. Now I don't have the slide filled out anymore, but when we titrate a weak acid, we come up with a, both of these running out at the same time. It was 0.004 and 0.004. So both these run out to 0, and we just have the conjugate base present. So anytime you have a weak acid that you're titrating, at the equivalence point will always be basic. Why? Because you don't have any acid left. There's no hydroxide that remains. However, you have the conjugate base of the acid that's present. And that has a concentration, and that will just be the conjugate base in water. So we worked this out. We found that the pH was 10.08. You should have that from yesterday. And we'll see a graph of this at the end after I do a couple other data points. But I do want to make it very clear. And I did this with the strong acid too, but you probably just took it for granted that for strong acid titration, the equivalence point pH was 7. When you have a weak acid titration, the pH is always above 7 at the equivalence point. That's because only the conjugate base is present, which is a base.
Mr. Moore, what are your thoughts on like caffeine, like coffee?
Thoughts on it?
Yeah, like do you like coffee?
I like coffee. I drink coffee socially. I'm not one that has to have his coffee. I'm a social coffee drinker. Like if we have a meeting or whatever and there's coffee, I like coffee.
All right.
Now here's what you do. You put hot chocolate and you put it in a coffee cup or something.
That's what Izzy always does. Oh my gosh, Joe and Izzy would be having a real bonding moment right now.
So yeah, like my big mug is just water.
I see. I was curious. Yeah.
What are your thoughts on coffee? Well, it's fine.
Pretty well.
I approve.
It's an addictive substance.
I don't know. Some people are very against it.
Oh yeah, no, I think coffee's fine.
People who are against it are just meaners. I don't know what's wrong with them.
Against what?
I don't know what's wrong with them.
Against what?
If they don't like coffee.
I know.
I get it.
Oh,
like,
are
it's
weird?
so
Is that what you said?
helpful.
Yeah.
Yeah.
I know these people like sleep.
No.
Yes.
There's,
Imagine that.
yeah. Of course, there's all the energy drinks and caffeine pills and things like that.
I mean, the energy drinks are really bad for you.
Yeah, I don't know. You know, I think the energy drinks are still new enough that we don't really know the long-term effect. Like, there's kids these days that will drink energy drinks every morning, and you know, when they're 50, is their liver going to be shot? We don't know yet because it's still new.
I've seen this video on Instagram or Facebook or something where like this guy does stuff with like Red Bull and stuff. It's whack. Some of it seems fake though, but like it doesn't seem good.
Yeah, time will tell. That's just what happens. Okay, so I'm going to come back and we're going to see the graph for all this in a moment. But let's go on. We're going to do two other data points. We probably don't even need to do two. We'll just do the last one for humor. But I want you to check out. We've just hit the equivalence point. Now this data point is going to be one past the equivalence point. And we do have to understand what happens with this, even past the equivalence point. I mean, the equivalence point is the interesting part. It's the worst to calculate the pH. But past the equivalence point, let's take a look at what happened. 0.004 moles of this is what we originally had. The hydroxide at this point, 0.005 moles have been added. And the OCl started at 0. So now the limiting reagent is the weak acid. That goes to 0. But we have an excess of hydroxide, 0.001 mole. The OCl, of course, goes up to 0.004 again. That's the amount that the acid went down. in this data point, there is a concentration of strong base still, 0.001 moles, and a concentration of weak base, this conjugate here. Now I want you to know this, and remember, you might want to write this down for yourself. When you have an excess of strong base, so our solution right now has hydroxide, just straight hydroxide ions, plus some weak base, which would tend to produce hydroxide ions. Anytime you have a strong base mixed with a weak base, just ignore the weak base and take whatever the concentration of strong base is and use that to find the pH. So, past the equivalence point, for all points past the equivalence point, neglect, this dominates the pH. This one, you can neglect. In the last data point, we had to pay attention to the conjugate base because that was all that was in there that could affect the pH. But now that we have strong base, this produces so much more hydroxide ion than the weak base does. Just neglect the weak base. Charlie?
So this is only for weak acid strong base titration?
Say that one more time.
So like where you neglect the conjugate base, is that only for weak acid strong base titration?
Oh yeah. And it's only when we're past the equivalence point.
Right.
Yep. Okay, so if we really only care about the hydroxide concentration for the pH, that's all we'll do. Now remember, and you're going to be tempted to do this when you have to calculate the pH. You've done the work here, and you come up with 0.001 moles. Don't just take negative log of that. We need the negative log of the concentration. This is just a mole. So watch out for that because it is easy. We're so used to ice tables that have concentration in them. I always give questions like this on the quiz. What's the pH of several data points? One of them is past the equivalence point. It's a really common mistake for people to just get the moles and take the negative log of it. So watch out for that. So anyway, you need the hydroxide concentration, which is a mundane task now. We've done this so many times. The moles over the total volume, which is 90 milliliters. So yeah, get the hydroxide concentration, take the negative log, that's the POH, and then take the, well, let's subtract 14. And we get pH of
12.05.
12.05. Awesome, thank you. All right, so I'll write it just over here. pH is 12.05. Now we haven't seen the graph yet. If you remember, when you have a strong acid titration, the equivalence point is this huge increase. You go up about 10 pH units when it's a strong acid titration. When we have a weak acid titration, I want you to notice the last 3 data points. We had that thing in the middle. This one was, let's see, 7 point, what was the pH of 30 ml?
30 ml, that was 7.94.
7.94, okay. So it went from 7.94, the next data point was the equivalence, 10.08. So we had a jump of a couple of pH units, and then it continues jumping up to 12.05. So we went from about 8 to about 12. So you get a jump of about 4 pH units. You notice it's a lot less than what we had with the strong acid titration. Yeah?
How do you know which one's the equivalence point?
Oh, the equivalence point is the point at which...
Like just using the data. Like just using the pH. Alright, keep on talking. Keep talking.
You don't know just from the pH unless you do the graph.
Okay, yeah, that's what I thought.
Yeah, and I'll show you at the end of this, we'll take a look at the graph. Yeah. I don't think it's necessary. Are you okay if we don't do another past the equivalence point pH? We know how to do that now.
Oh, I did it anyway. pH
What'd you get?
12.30.
It'll go up very slightly after that, but it's pretty well leveled off from there. Okay, so this is what we expect to see. Every weak acid doesn't look exactly the same, but weak acids generally are going to have this shape. Now this is a different graph. There's a couple of things that are noticeably different between this and the strong acid titration. First of all, the strong acid titration started lower, Normally they'll start around 1 or even less than 1. And the strong acid titration gradually went up right from the get-go. This one, you'll notice, jumps at first. See that jump? We noticed that too. The first, I think our first point was, what was our first point? 4 point something. And then it jumped up to almost 7. In one data point, it had a jump. And then it levels off. Do you remember why it becomes flat like this? What's happening in this region between the beginning and the equivalence point?
They're basically buffer.
It's a buffer, right? It's a buffer, so it resists changes in pH. So it levels off, it stays pretty constant until we get to the equivalence point, then it shoots up. So if I just gave you the graph, you'd say, okay, the equivalence point happens at around 25 milliliters of the base add. And notice the pH. The pH, we would say, is just the middle of the vertical region, right about there, was the pH at the equivalence point.
That's what I was talking about. You just kind of estimate.
Yeah.
Ah.
I kind of figured that was what you meant when you have the graph. Yeah, just estimate. Yep. Yeah, and then past the equivalence point. Now it doesn't. It usually will level off more and go like that. It doesn't. It appears like it keeps rising up pretty quickly. It doesn't. Yeah, this was a different acid. They're telling you what down here what it was. It was acetic acid. So it didn't start in the same pH as HOCl did. But they have generally the same. You always, for a weak acid, get a quick jump, and then it levels off, and then you get an equivalence point above 7.
So, like on the test or something, would we ever have to look at the graphs and be able to estimate it? For, like,
Yes, yes. I would give you a graph and ask you to analyze it. I could ask lots of questions about this. Yep. It's an approximate pH, yeah. Yeah. It's about the equivalence point pH. Anything else about that? We've seen now 2 titrations. We saw a strong acid titration, then we saw a weak acid titration. We have a third one, a weak base titration. Now for the weak base titration, I want to go through one data point with you together, and then I'll have you come up with some of the data points after that. We'll keep things moving with that one. So let's take on one more titration curve. I said we're going to do one together. I want to do 2 together. The first one is with no acid added, and then the second one we'll do where we have at least some acid in there together. Then I'll set you loose.
Pyrite was one of the ones I saw at the mineral museum.
This is not pyrite.
I know, but pyrite, pyrite
yeah.
just reminded me of pyrite.
Yeah. Fool's gold, they call pyrite.
Yeah,
Looks like gold.
definitely.
Would you be able to look at the formula for pyridine and tell that it's a base?
What is
Yes.
the
Yeah.
formula say?
C5H5N. There's a comma after. I don't know if that looks like a number
Yeah, that's
from
what
there.
it's- okay.
Yeah, it's just C5H5N. Is that a base? Yeah. Not only does it tell you the Kp, but you need to know that a neutral nitrogen compound is always basic. Yep. I've had several questions, people coming up, just starting the homework, not sure still whether a formula represents an acid or a base. You need to know that. So remember, the neutral nitrogen compounds are basic. And when I say neutral, I just mean it doesn't have a charge.
You know, that's easy to me when I don't know my strong acids.
Yeah, I'm going to be disappointed. You know them. You don't even try to kid me. I know you know them.
You overestimate me.
No, I don't. Okay, we ready? Should we take this on?
Make it sound like the charge.
So before any acid gets added to it, we just have pyridine and water. I said, yeah, pyridine and water. And so we have a weak base. We write out the equilibrium chemical equation, set up an ice table, solve for the pH. This is going to be 0.1 minus a small x value, that's x and that's x, so that the KB, which is 1.7 times 10 to the negative 9, sorry, I wrote that funny, I was thinking that was a fraction, that's not a fraction, equals x squared over 0.1 minus a negligible x. So when we solve for x, that's the hydroxide concentration. Get the POH and then the pH. And if you can determine that and report out, just yell it out when you have it.
Concentration?
Just the pH is fine. We can all come up with pH. 9.12 sounds right. Yep. Yeah, just looking at this, multiplying the 0.1 out, we get 10 to the negative 10th. Then it's, take the square root, you're going to get something like 1 times 10 to the negative 5th. So the POH is about 5, therefore the pH is about, pH is about 9. Sounds good. 9.12?
Yeah.
Can I get a witness?
Yep.
Okay, so this is a base solution. We expect the pH to be above 7. Our first data point after the, the first addition of strong acid now, when you add a strong acid or base, the reaction always goes to completion. I've said that a lot of times, and I'm hoping that that sinks into your brain. When you add a strong acid or a strong base, the reaction always goes to completion. Hydrogen ions, hydroxide ions, they are going to react completely. They don't come to a nice sweet equilibrium. They are very, very reactive things. So they go to completion every time. All right? So we're going to see a similar kind of thing happening as what happened with the weak acid. Just do the stoichiometry here. The pyridine, we have 0.004 moles of that. The added hydrochloric acid is 0.001 moles of that. The conjugate acid starts at 0. So limiting reagent looks like it's hydrogen, so that goes to 0, that goes down to 0.003. And this goes up to 0.001. What do we have? We have a buffer. Yes, use the buffer equation. Yep. And this is going to be true for both weak acid titration and weak base titration. Between the first point and the equivalence point, use the buffer equation. Yeah.
I see. Okay.
Good?
Yeah.
All right. Okay, so now when we use the buffer equation, remember the formula, pH equals pKa plus log of bah. This term right here, pKa, I mean it, pKa. So what you're given in the problem is the Kb of pyridine. When you're using the buffer equation, you got to find the Ka of its conjugate acid. The buffer equation will always use that. The rest of it, we know. Just make sure you know which one is the base and which one's the acid. Now you can always just find the pKb and subtract it from 14 to find the pKa. That's easy enough to find.
I think the Ka is 5.9.
I got 5.23 for the Ka. pKa. Oh, no. Oh, my gosh. 0.003 over 0.001. Okay, and away we go. We can calculate the pH, and I bet that pH is going to drop significantly. What do you get?
5.70.
5.7. What? That's quite a jump. it was basic at the first data point, 9 point something, and then it falls with one little addition of HCl, falls all the way to 5 point something. pH is 5.70.
Yep.
7.1. Now that's quite a drop. But that's only because pyridine is a very weak base. So the HCl makes that change. At this point, I'm going to ask you to calculate the pH at several data points. Now we have this. Our first data point I'm going to put up here, first two data points. We had what, 9, what was the first one?
0.
9 point what?
Oh, the pH was 9.12.
Okay, so let's see. That's about 9. So 9.12 is roughly there. Okay, and then when 10 milliliters were added, it fell all the way down to 5.7. So I'm going to do my best to estimate this right about there.
5.71.
Of course, 5.71. I counted for the 1. All right, Team Rohan. Can I have your group, your row, do when 20 milliliters of HCl are added? You guys come up with a pH, agree on it, and send one person up here to draw the dot in there. Team Joe, would you do 40 milliliters?
Yep.
Wait a minute. No, it's 30 milliliters.
Okay.
Yeah, because you guys have 20, right? Team Joe has 30. Team Neha, would you do 40 milliliters? I had to say that 40 milliliter one. It needs a smart group. That's you guys.
Thank you.
I just made fun of you guys. I burned you bad. Nobody even said anything.
Okay.
I said, no, I don't want you to do 40. I want them to do 40 because I needed a smart group.
I think you're not.
I mean, yeah,
You never said you wanted the right answer.
So you got 40. Why does 40 need a smart group? Can you tell? That's the equivalence point, yeah. You guys have 50 milliliters, and would you guys do 60, and would you guys do 70 milliliters of HCl? Yep. So yeah, does everybody have the information they need? I'll click off of that for a moment. So yeah, get a pH and agree on it. I want all the people in the group to agree. And then one person comes up and draws the dot.
Yeah, look at the one from yesterday.
Alright, guys. I got 4.75.
I got 4.7.
Which one did you say?
I got 4.7.
I got 4.
I also thought that.
Yeah, I got 4.7.
Oh, what?
Yep. Do you have a pH?
We're reading. So I got 5.
It really is an art writing on this board.
You don't have 20, you get 25. Or no, you got 30. 30.
Uh-oh.
You got 4 points something?
5.75. I know that's like really close to the middle, but hey. Mr. Redmond, this. Yeah, now I can calculate all the other data points.
Oh, this one. They're the same. They're the same. The one that you gave us is 40.
Oh,
Yeah. So then he, yesterday he said that if it has the same amount, then
Yeah, that'll be one.
it has this,
Yeah, we did one with the same amount of voltage.
No, it's 0.004. Oh, this was 0.0.
Can you find it?
Okay, right here. Oh, that's the question. Okay, so you have to go through titration this time. Yeah. Okay. I see it. So this one will
KB,
Oh, I see. Okay.
KB was 1.7 times 10 to the negative 4.
We were 70.
4. Right here. There's a design. Sorry.
Yeah, we're at 70.
What is the pH? Ask your group.
I vote yes.
Oh.
Yeah, it matters.
Wait, yes.
The class is dependent.
Mary, just go for it.
Is that good?
Not me, it's like
Perfect.
That is better.
yeah.
It's weird because the 5 is in between those two lines, so yeah, you have to estimate from there.
Wait, why am I the only one that uses like I just made you use the
Oh, wait, yeah, buffers is more after.
Why am I the only
You did fine. You did fine.
No, but like I'm the only one that uses green.
I know, it was okay.
It's
You're
okay,
your own
Mary,
person.
Garrett's be different.
But green's such a lost my
No, what's ugly about it? Eddie's got green on. He's telling me Eddie's ugly. What did you guys get? What did you guys get? Oh, do you have an answer? What did you get?
No, use green.
That seems perfect. Given what the other points are.
Yeah.
No, and then there's the part where you just play like your camera. I wanted to get it by the time I got my phone.
Mr. Moore, since it all ends up with for 40 milliliters, since it ends up with 0.004 moles of the conjugate acid, wouldn't you basically have to do an equilibrium reaction with the molar?
At the equivalence point?
Yeah.
At the equivalence point, yes.
Yeah, okay.
Yes. So that's the worst part. All right, gang. Very quickly, I do want to remind you, the equivalence point, you notice our group that took the longest was the equivalence point group. That is the worst data point to find the pH of. Why is that? Is because only the conjugate acid remains, so you've got to go back and once you do the stoichiometry, you've got to go back and do an acid equilibrium ice table and find the pH from there. Yeah?
When do we go back to the point, go back to the equation versus when do we use the pKa?
The buffer equation happens up until the equivalence point. Because until the equivalence point, you have the base and its conjugate acid both present.
But both have the same amount of molarity.
They don't have to have the same amount. As long as both of them are present, then you can use the buffer equation.
But when is it equal to, when is pH equal to pKa?
Oh, that's only at the halfway point. The halfway point, the equivalence point happened at 40 milliliters. So the halfway point is what is the pH at 20 milliliters? Yep. And you guys had 20 milliliters, right?
Yes.
Yep.
The pH was equal to the pKa.
Yes.
pKa was 5.23.
5.23.
Yeah. So, boom, there it is, 5.23. Yep. Very well placed, Dot. Do you have a question?
Yeah, I checked 40 milliliters group and I apparently got a different answer.
What'd you get?
I got 3.27.
Okay. Hate to do this, but let's go ahead and do the pH at the equivalence point. At the equivalence point, I'll do this very quickly. We had, I'll just put pyridine, P for pyridine, plus H plus yields HP plus. You had 0.004 of that, 0.004 of that, and 0 of that. That went to 0.004 while the other ones became 0. Right? So the acid, so all you have is a weak acid at this point. The acid has this dissociation reaction. No. Not minus, it's just P. When we do the ice table, you don't just put 0.004 and you put the concentration in, which is 0.004 over the total volume, which is 0.08.
Which is
So what you did?
0.05.
You just use 0.004? Yeah, the ice table's got to have the concentration. Did everybody hear that? Not just the one row that did it, but make sure that when you, the equivalence point, you got to spend some time with it, invest your brain into it. Yeah? There's a lot going on at the equivalence point. So you got just the weak acid remains, the conjugate acid does. So you have to write the equilibrium dissociation of the weak acid in a separate ice table. And ice tables only include molarity. So this concentration is 0.05. And that was X and that was X. So when you solve for the X, you got to use the Ka value, not the Kb value, but the Ka.
It was 5.9 times 10 to the negative 6.
5.9 times 10 to the negative 6th
Yes.
equals X squared over 0.05 minus a small x. So yeah, solve for X that way and then take the pH. Satya?
Why can't we use the concentration like molarity for the top equation?
Why can't you use molarity up here? The molarity changes, like the amount of hydrogen ion you're given. Yes. If you want to, you can. I prefer to do the stoichiometry in moles. You would not, let's see. You would have to dilute both the H plus and that. You'd have to use the dilution formula for every data point. Because both of the volumes are changing, so you'd have to do that. And it wouldn't dilute by the same factor every time because you're adding more and more of the titrate. I think it's cleaner to use moles. I've always done it with moles, and I think that you'd like to better. Okay, everybody good with that? It's time?
So whenever we do the equivalence point, you have to do 2 recipes. Is that how?
Well, you have to do the stoichiometry step and then do a weak acid ice table.
I didn't do it to be
Or if it was a weak acid you're titrating, you have to do the weak base type ice table. And it's only at that point that you have to do those 2 parts for it. Have you?
You still don't count the X though, like.
This minus X, you don't count it because the K is so small that X is really small.
Right.
Yep.
I promise I didn't do it to be mean.
I was going to ask the whole class to calculate the pH at the equivalence point too. So we don't feel bad or have any animosity, right?
But what is
We're all
the
good.
pH?
Okay, so the pH was 3 point something?
It was 3.27.
2.3? 2.7. All right, so I'm going to erase all that so we have a nice, pretty graph. And this pH, Mary, I'll use green so you don't feel so lonely. 3 is halfway up here, and then 0.27, I'm just going to estimate right about there. Okay. So that looks good. I'm going to go ahead and draw a smooth curve through this data. Whoop. I'm going to not. Okay, so I want you to see that when you titrate a weak acid or base, you don't necessarily get a nice sharp equivalence point vertical region. Look at that. It was just kind of a change in inflection. If you've learned about inflection. Some of us are in calc, right?
Nope. Not
Yeah.
yet.
Yeah. Yeah.
Yeah, is that you?
Yeah. I love calc.
It's a pretty great thing. All right, so I'll just, and then this is just more of the same. I told you that the titrating a weak base is parallel to titrating a weak acid. It's all about the same. So yeah, when you have a weak base you're titrating, the equivalence point is acidic. Yes?
Like, why do we find the equivalent point? Like, what is it used for?
No, I have an answer. I'm just making sure that I say the right thing.
Yeah.
When you do a lab next week, you're actually going to do several labs. It's going to take us about a week to do multiple labs. One of the labs is you're going to have a weak acid. You're going to titrate it, but you're not going to know what the weak acid is. It's an unknown acid. But you can titrate an unknown acid with a base, and you get a titration curve, right? So when you have the titration curve, I'm going to take you back to the weak acid. So we're going to wind up with a curve something like that. If I ask you to try to identify the acid, how would you do it with the curve?
You could find, well, one, you could use halfway to the equivalence point to find the KP or KB, or...
Say that one more time louder. Listen to what Joe said.
For the halfway in to the equivalence point, you could use it to find the KP, wait, the PKA, or
Yeah,
the
stop there. That's exactly right. Before you go on, remember yesterday I told you there was something very special about the halfway point? The halfway to the equivalence point is the point at which the pH equals the pKa. Because the acid and base are the same at that point, so that part of a buffer equation cancels out. So in this graph, so you have the graph. You have to know what the equivalence point means and what it is. So it's right there, the middle of the vertical region. That took 25 milliliters of base to get to the equivalence point. Therefore, halfway to the equivalence point, which would be 12.5, at that point right there, whatever the pH is, if I just go over there, the pH is right about there. Whatever the pH is, that's the pKa of the acid. Because at the halfway point, which is right there, the pH equals the pKa. So we'd be able to identify what the acid is from this graph. We had to know what the equivalence point was, and then halfway back is where the pH equals the pKa is. So we know what the pKa of the acid is, now we can identify it. So that's part of it. Another part of it is just knowing how the concentrations affect what the pH is. So we do have to make a big deal about the equivalence point. We need the pH of the equivalence point.
Yeah, no, I was wondering.
So yeah, that's a long answer to your question, but yeah, every part on this graph is significant in a different way. Yeah. Evie?
Can you go back to the weak base strong acid graph? Is it always gonna look like kind of like a W? Like
Yeah, if it's a weak base, it will.
Okay.
Yeah. You're going to get a sharp first point change, and then it levels off a little bit. It's a buffer in here, but then you get a drop, a vertical.
Okay.
It's not very vertical, but yeah, that is going to always look like that. Now, the weak acid kind of looked like a W too, didn't it? It's if we turn our heads about like that, then it's a W. Keep going. You got to go about what, 135
or you could
degrees,
just say it to M.
and it's a W. Yeah. I'll help Izzy out. Izzy, if you do this, then it looks like a W.
Oh wait, Mr. Moore,
Yeah.
have you ever like recorded something and then listened back to it to hear your own voice?
I do sometimes, but I don't
I
like it.
dislike it.
Yeah,
It's
yeah.
so bad.
Does anybody like listening to themselves?
So terrible.
It's like, I don't sound like that. Oh, yeah, you do. And somehow you think people are going to judge you and think you're an idiot because of the way you think you sound. But no, that's all we know. So, I know.
When you hear
I sound
yourself
like
talk, you don't sound as bad. When you get in here, you're like, oh my god, stop.
I know.
I don't want to do this again.
Oh, wait, I wasn't. Thank you.
I don't think you sound like a guy at all. Oh, you're working on it? Keep trying.
And you said you need smart people for
Okay, so we have just a few minutes left. I have a very quick question for you, and then I've got. Oh yeah, we got to do that too. Now I have told you the wrong thing twice, and I need to make it right finally. A couple of days ago, we did a problem. I think it was number 41 or 48, something in the 40s. I said, this is going to be on the quiz, and I realized, oh shoot, no, that's not the one that's going to be on the quiz. I told you, no, number 54 is going to be on the quiz. Then I looked at the assigned problems. Oh shoot, number 54 is not on there. So now I'm going to tell you the right thing. The right thing is number 53, which is just like 54, is going to be on the quiz. Now, I'd like to show you how to do that one. Okay. And then still I'm going to have a bunch of people get it wrong. But don't let that be you.
That's not encouraging.
Claire, pay attention.
Right, yeah.
This first quick one. Is this a weak acid being titrated or a strong acid being titrated?
There you go.
Wait, no, weak acid. It's weak acid.
Because the other one we just looked at, it was.
Yeah, we.
No, strong acid, strong acid.
That's what I've been saying. Otherwise it'd be 7.
Well, we know the base is strong because the other one.
Emily? Emily? What is it? The equivalence point does not have a pH of 7.
Weak acid.
It's above 8. It's like 9. So the pH is 9 at the equivalence point. Is it a strong or a weak acid?
Weak acid.
It's a weak acid. Yeah.
Oh,
Wait, strong acid, strong base will always be a 7?
yes.
Yeah.
Okay.
Always. Okay. I have tried to make a really big deal of that. Now, do you see why? We got to know whether it's a strong or a weak acid by the shape of the titration curve. Notice also, you could have also seen from this first part, remember, the strong acid did not have that quick jump at the beginning. A weak acid always does. So you get the quick jump, and then it levels off, and then you have a basic pH at the equivalence point. A strong acid would have started low and just gone up very gradually with no quick jump at the beginning, just go up very gradually, and then you get, remember, strong acid is going to have a pH jump around 10 units when you titrate it. This is just a little bitty, I mean a jump of what, 4 or 5 pH units. So that's what I want you to be on the lookout for. Okay, now let's get to this one. Number 53. Now for my third try, this one is accurate. I already have made the quiz. This is on the quiz.
If I just
With a different number. I'm not going to ask you to do the different number.
We can figure out what number.
Same number? Oh, different.
What are you going to try to do, Aditya?
Retrace the fingerprints on your keyboard.
Oh, and then you'll have it.
Yeah. I know.
Okay, so the question is, how many moles of sodium hydroxide must be added to 1 liter of 2 molarity acetic, not acetic acid. Time out, don't write the question. Just, I had 54 on here. There we go.
Oh, wait.
Yeah, sodium acetate was number 54, so I had to change that. If we have 2 molar of acetic acid, how much sodium hydroxide needs to be added so we make a solution buffered at pH of 4?
So a buffered solution that has a pH of 4. Wait, so it's a buffered
Are you
solution.
joking? Like,
This is number 53.
No, on Tuesday.
There is a quiz on Tuesday.
I
If-
don't know. This
If I
guy,
don't
he's
give it to you
playing
on
with us.
Tuesday, I'm not giving it to you.
But how come the other classes don't get a quiz?
Yeah.
No, they do.
They
Everybody,
do.
all my classes have a quiz on Tuesday.
I prefer not to test
All of
this
us
thing.
get on that one.
If I didn't tell them, I didn't mean to not tell them, and I'll just give them a pop quiz on Tuesday.
Wow, that's evil.
Oh
That is
my
evil.
God.
Wait, so it's
That's scary.
No, but I'll tell them.
Even the idea of that is horrifying. But
I'll give
Mr.
him
Moore,
a pop quiz. I'll
The
tell
idea
him ahead
is
of time.
it's coin stall day. If you can stall me for most of the hour, then I won't give you the quiz. The quiz is about a half hour long. I would give it a normal quiz time.
Oh, so kill all your coins 30 minutes in. I see.
No, we just have to.
wait, no. No, but you don't have to give it.
I'll warn you, I'm really fast at counting coins.
Not with your elbows, you are.
Oh, my elbows are the fastest coin counting elbows. Okay. If you can at least write a chemical equation for this one, you'll be doing great. Can you write a chemical equation? Do you have an equation?
I have one. I am not sure if it's correct.
Okay, let's see. Does your equation react this weak acid with the strong base, sodium hydroxide?
Yes.
Yes.
Wait, can you write it?
Yep, I will.
Yeah, I don't even have to study for
The
this.
sodium hydroxide is a vicious dog. It's going to attack that weak acid and rip as many hydrogens off as it can. So the acetic acid, HC2H3O2, reacts with the hydroxide. I'm leaving the sodium off. And the arrow is one direction.
Ah,
One direction. We like
can
one
we have the
direction, right?
Ka of?
Do you like One Direction?
Yeah, I like one direction.
Another clip you should find.
Okay. How does that look?
Like what I have.
Yeah.
Excellent.
I almost have.
Great.
But we can leave.
Seriously, you're doing really well if you can write the chemical equations.
I think I just got lucky.
All right. Now, how does that help us? Let's see. We have 1 liter of this, and the concentration is 2 molarity. And how many moles of sodium hydroxide? That's what the question is asking. We need a pH of 4. Did you catch this word?
Buffer equation.
Can we have the Ka?
Bah, bah. We need that. We can use the buffer equation, yes? If it's buffered, that means we can use the buffer equation. That means that this solution at the end has to have some acetic acid still, and it has to have some acetate. Yes?
Wait, don't we have
I'm going to say that again. Can I just say that one more time, then answer your
Be
question?
my guest.
Thank you. This solution at the end must have some of this still, and it must have some acetate on it if it's buffered. Go ahead.
Don't we need the pKa value?
You do. Yeah.
Can we have it?
Yeah,
Yes.
That's, okay.
Yes.
Thank you.
You do need it. So, before I give it to you, I just want to make it clear, and make sure that you agree with this, hydroxide must be the limiting reagent.
Yeah. Well, it has to be acidic, so.
Yes. Hydroxide, but it's got to be buffered, so you can't run out of acetic acid because you have to have some for the buffer. Yes?
Say that again.
You can't run out of acetic acid because you have to have some at the end to make it a buffer. A buffer has an acid and a weak acid and its conjugate base. If I run out of acetic acid, I don't have a buffer. I'll just have a base solution.
I see.
All right. Now, that's the key to the problem. I'm going to erase what I had here because when I see that it's a one-way arrow, I'm going to use moles for my stoichiometry. So I'm going to go ahead and just say 1 liter of 2 molarity solution means I have 2 moles of acetic acid. I'm going to run out of time. I owe you that fire demonstration. I'll do it next week. Okay, so anyway, we start with this. We start with 0 of the acetate ion, and we're starting with 2 moles of this and some unknown number of moles of OH, which we're trying to find. Yes?
Yeah.
So if we agree that the limiting reagent has to be hydroxide so that this doesn't run out, then I think we need to agree that the X goes to 0. If it was the limiting, that means it all got used up. So if OH went from some amount X to 0, that means that the acetate ion went from 0 to X. Yeah? Yeah. So what happened to the acetic acid then? It went down by X to 2 minus X. Use the buffer equation. Your Ba is X over 2 minus X. Solve for X. You got it.
You still haven't.
I'm going to warn you that the solutions manual, if you look at the solutions manual, your head's going to be spinning. You're not going to know what they're doing.
You still haven't given us PK.
Oh. Demanding.
Tell us to solve, but we can't solve it yet.
Oh, that's the one that.
Okay, I'll solve this thing.
Sorry that I didn't give you the KA. Yeah.
It's okay.
We forgive you.
I'll put it in the problem too. But yeah, so just write down for yourself. That's the key to the problem, is knowing that the hydroxide runs out. Therefore, everything else changes by X. You have everything in terms of X. Solve for X. What? Sounds good. I don't know what it is. I'm just telling you how to do it. Don't do it the way the solution manual tells you how to do it. Sorry.
Have a good weekend.
Have a nice weekend, everybody. There's your friends. Goodbye, everybody. Have a fine weekend. There you go. Go on to you.